Right, so we'll start with today's lecture. So yesterday we talked about the three difference methods: finite difference, forward difference, backward difference, and center difference. Are these methods clear? So we applied that to the first order derivative. So what we'll do today is, very quickly, we'll apply this to second order derivatives, because that is also what we encounter in our equations. So in a one dimensional situation, what you will have is you will have d2 phi by dx2. So let's figure out how to discretize this into a difference form, difference of phi values at different x points. So let's say we want to calculate this at a point xi. So again, the same kind of graph that we have been drawing. So this is your curve. So we have xi comma phi I point, and I want to figure out a way to discretize this second order derivative this time. So we said that we have intervals in our x axis rather than having continuous distribution. We have xi, and the next point that we'll have in the interval will be xi plus delta x. Similarly, the previous point would have been xi minus delta x. So these are the discretized values of xi's. So right now we are assuming that delta x is constant, or it does not change with x. So it's homogeneous. So yesterday we learnt the center difference method for first order derivative, and second order derivative is nothing but the first order derivative of the first order derivative. So what I can write this to be equal to is, it's d by dx of a function which is d phi by dx at the point xi, right? So let's call d phi by dx. Now since phi is infinitely differentiable, so d phi by dx, all the derivatives exist. So d phi by dx, I'll now for simplicity I'll call it eta. So basically the second derivative of phi with respect to x is d eta by dx. So let's since we know the methods to discretize the first order derivatives, so let's do that. So let's find out d eta by dx at the point xi. Using center difference. Anybody wants to help me out? What will be d eta by dx? So it will be, yeah, eta at I plus 1 minus eta at I minus 1 upon 2 delta x. So that's one forward point, one backward point, right? Can I also do this? Can I call it I plus half, I minus half, and this delta x? I know that there is no point that exists at I plus half, but if there was a point, I could have done it, right? So I plus half is somewhere here, and this is I minus. So this is I minus half, and this is I plus half. The index, okay. The x location is xi plus delta x by 2, and xi minus delta x by 2. I can do that to calculate the slope at the blue point. So I can use one point which is half an interval away, and then I can join these two red points. That also gives me a good estimate, right? Does everyone agree that I can use this? I know that I plus half and I minus half points do not exist, but if they existed, I could have done it. And you'll know why I'm doing this, or you may already have guessed why I'm doing this. Right, but eta is also something that we have to resolve. Eta is a partial step, so eta is d phi by dx. So let's work for eta at I plus half. So what is eta at I plus half? d phi by dx at the point xi plus delta x by 2. So, that is the value here. Now, to find the derivative value at a point, again I can use center difference, half a point forward, half a point backward. So, half a point forward is xi plus delta x, that is the point. So, this is phi at xi plus delta x, and half a point backwards is phi at xi divided by delta x. So, this is again center difference method. Center difference says that you take a point forward and a point backward, and then you divide that by the interval size, I mean the size of the interval of that particular situation. Similarly, eta at this boxed point that I have just shown at x I minus delta x by 2 can again be expanded using the center difference method. So, this allows us to write the discretization for the second order derivative using the center difference method. And the trick we used was that the center difference method for second order derivative is first order derivative or the first order derivative. So, you work in steps, and this also tells us why we use that half interval, because we could do that twice and then we could get 5 values at those discrete points where they are actually available or where they are actually defined for this CFD situation. Okay? Is that clear to everyone? Now, as in the first order derivative case, this is also order delta x squared accurate. That is another way to say it, or we say that the truncation error goes as delta x squared. There are different ways to say it. Okay, sometimes we say truncation error goes as delta x squared, sometimes we say the accuracy is order delta x squared big O. Okay. You may have learned that in your computer science course first year, big O. Okay, that basically they are the same thing. The error goes as some constant times delta x squared, that is called order delta x squared. Another way to say it is that this is a second order accurate scheme. Okay, so, this is a scheme to to discretize the derivative of second order. So it's second order accurate. So the idea, the word second order here means that is delta x squared. It's not the order of the derivative, because the first order derivative d phi by dx could also be discretized using the center difference method, which was a second order scheme. When we use the word again and again, you will get used to it. But for now, just make a note that second order accuracy is the same as saying truncation error is order delta x squared, or accuracy is order delta x squared. So I will leave it to you as a homework to show that this scheme that you have written here is indeed order delta x squared. And as I iterated in the beginning of this class, this homework is actually basically kind of an assignment or a tutorial for you. So you please you make sure you solve this, because these are the kind of questions you will get in your quizzes and exams. Okay. Good, well done. Okay, hint is very similar to yesterday, that you have to expand phi I minus 1 and phi I plus 1 around the point xi comma phi I using Taylor series. And when you do that, all you have to do is you have to substitute the expression of the expanded Taylor series form in this expression. Now remember, I mean, I have stopped doing that, but this is an approximation. We are approximating the second order derivative using this difference formula. It's an approximation, and that is the reason when we do the analysis for the error accuracy for the error order, we substitute the actual expression for phi I minus 1 and phi I plus 1 using Taylor series, and then we see that there is some error involved, and that error is what we are trying to identify in this homework problem. So I will stop writing this approximate, I will start writing equal to here, because that is what our discretized form is. But please remember the fact that this is equal to under the condition delta x tends to 0. For delta x finite, it is an approximation, and you can find the error now using in this homework problem in the form of delta x, and you will see that the error formula that you have, if delta x tends to 0, error will go to 0, and that is what we expect. Questions? And this whole exercise that we have done, starting from yesterday all the way to today till now, of converting derivatives such as d phi by dx or d2 phi by dx2 into difference forms. So for d phi by dx, center difference was phi I plus 1 minus phi I minus 1 upon 2 delta x, or for the second case it's phi I minus 1 minus 2 phi I plus phi I plus 1 upon delta x squared. So these all are difference forms, right? You can see that there is some sort of a difference between phi values. So this process where we have gone from derivative to difference form, as I said, is called discretization, and discretizations can be done in different ways. So this particular way is called the finite difference method. Okay, so derivatives are transformed to differences of finite values. So they call finite difference. It's called a finite difference method. So you'll see in the books there will be a topic called finite difference method, and then they start discussing all this. So rather than giving you the topic heading in the beginning, I'm telling you what this actually is called because of the way it looks. Okay, the differences. The other way is called something like finite volume method. That is also what we'll. So after the middle of the course, we'll start working with a method called finite volume method, which has its own benefits in terms of conservativeness and so on. So we'll learn both these methods, finite difference and finite volume. There are other methods also, finite element, spectral element and so on. They are beyond the scope of this course. Now, just a food for thought. So this can be considered the second part of the homework that I just wrote above. So will the center difference method that we just discussed for second order derivatives, will that be second order accurate if your delta x was non-homogeneous? That is, delta x interval sizes, the right interval and the left interval, they were of different sizes. Okay. So for now, till now we have been assuming that this interval size that we have, so we have an interval here and we have an interval here. They are both of delta x sizes. For this particular food for thought, just think of a situation where these intervals are of different sizes, let's say delta x 1 and delta x 2, and then when you are calculating or evaluating the accuracy of the scheme, the error of the scheme using Taylor series, just check if they are actually second order accurate or the accuracy depend on delta x being homogeneous or not. So that will also help you appreciate the benefits of keeping delta x homogeneous. Okay. So this makes us ready for moving ahead, for actually being able to, now that we have a tool to write derivatives in difference forms, we can start solving problems, or we can start discretizing equations governing differential equations. So yesterday we said we are working with we are going to work with elliptic equations first. Now many of you are in third year undergraduate and you have not done a course in heat transfer. Now very typical problem that we solve in elliptic equations is the heat conduction problem. So what I will do is, usually I do not do this in a CFD course, but I will very quickly model the problem. So we will start with the physical problem that we have, and I will show you the modeling process that allows us to go from that physical problem using some laws of nature or some conservation laws to a mathematical equation, and then we will start solving it. So that also helps you appreciate the process of modeling. Through heat conduction equation. So let's derive. So, derivation of the heat conduction equation. So, I am sure everybody has seen heat fins. If you see an automobile, you will see that around the engine you have these fins jetting out, and we also have a field that these are used to get rid of heat quickly, so that the engine temperature does not rise very high and the material starts melting. So, it is for getting rid of heat as quickly as possible. So, we want to maximize the amount of heat lost per unit time. Okay, so, that is the units are watts. So, the amount of watts we want to lose is higher if we have fins. Okay. So, let us analyze the situation of a fin. So, we will keep it simple, we will just talk about a single fin rather than having, you see a cascade of fins, lots of them are there. So, we will consider a situation of a single fin. So, this rectangular fin is a fin that is jetting out of a surface. So, this is a surface, and what you did was you attached a fin to it so that it can lose heat. Now, in this situation, typically it's a problem where we want to analyze the temperature along the surface or along the length of the fin, because if you have temperature, you can find almost everything from there in terms of derived quantities. So, the unknown variable that we want to solve for here is temperature. Let us keep that in mind. Now, this is a 3-dimensional situation. The fin looks 3-dimensional, but it is a pseudo 1D problem, in the sense that there is a coordinate x which is from the surface along the length of the fin. Now, this fin is let us say that it is very long as compared to the thickness of the fin, and it is also very deep. So, that way what happens is that the temperature variation is mostly seen along x direction. You will not see much of a temperature variation along this direction or along this direction. So, along the depth it is symmetric, that is the reason you are not seeing that. Along the thickness it is so small that the temperature gradients, because it is such a thin fin that you will not see much of a difference between the top surface and bottom surface. Okay. So, this is an assumption that we take, although it might be finite in terms of temperature differences along different directions, but let us take an assumption that in this situation the temperature only varies as a function of x. So, temperature theta is only a function of x, and you have done this in the past in your mechanics problems, for example, in physics, where you took let this be only a function of x and you start solving the problem, right. So, this is an assumption that we take. So, this makes it a pseudo 1D problem. Now, how do we get the equations? So, for that we always, once we have the geometrical understanding of the problem, we need some physical laws or some laws that we can use to formulate the equations. So, you have been using Newton's second law of motion mostly in mechanics situations. So, here since it is an energy problem, we have to understand what is the phenomena that is happening. So, if I look at a very thin section, so let us say that somewhere in the middle I look at a thin section of the fin, then what is happening is, and since it is a 1D problem now, so I can just draw the section like this, and this is your x direction and this is the surface. So, this is x, and this thin section that I have considered is delta x thick. So, what is happening is that there is some amount of energy that is entering this section, and that is because of heat conduction. Heat is getting conducted from left to right. So, heat conduction in, then some energy is lost, heat is getting conducted out, and the major reason you have a fin is you want to have some heat loss from the surface. That is the whole idea of having a fin, right? You want to increase the surface area, and that heat loss from the surface is something called convection. Right. So, convecting. out from the surface. So once we have an understanding of the physical phenomena that's happening here, now we need to know some laws associated with conduction and convection. How do I quantify the heat getting conducted in and conducted out and convected out? Well, you already know those laws. I'm sure for convection you remember Newton's law of cooling. So Newton's law of cooling says that the heat flux, so there is a term called flux. So heat flux due to convection is H times delta T or delta theta in this case. So theta of the surface minus theta of the fluid around it, surrounding. Surrounding is you have fluid. Convection is because of some air blowing around the fin surface and so on. So it's we call it fluid. Let's be clear, it's the fluid temperature, not the solid temperature. And theta s is for the solid or the surface temperature. Now in this case we calling surface, but we are saying that the temperature on the surface and interior is all the same. The only variation is along x direction, not along the thickness of the fin. Okay, so theta, I don't even need to write s. I can simply write theta at any distance x that we are considering, because remember that this element that we have taken here is at a distance x. So as you change x, your heat, conduction, convection both will change. Now this is flux. So flux has units of watts per meter squared, because you see the more surface area you give, the more watts you will lose. So typically we talk in terms of watts per surface area or meter square. That's a better quantity to talk about. So if you want to calculate the watts, then you have to multiply that by the surface that is available for convection. Okay. Now for conduction, Fourier's law of heat conduction. So that was given by Fourier, the mathematician Fourier, when he was solving the problem of heat conduction. In that process he also developed many mathematical tools called Fourier series and so on. They are all developed to solve this problem only. So Fourier was, he did not just model the problem and leave it, he developed mathematical tools to solve it as well. That's amazing. So conduction is where we use the Fourier's law of heat conduction. Now if you have not studied this, you will study this. You will study this in your heat conduction course or heat transfer course. So this law states that the heat flux because of conduction is minus times a constant k times d theta by dx. We have an intuitive feel for it. Heat flows because of temperature difference. So there has to be a d theta by dx. Now d theta by dx, if it's positive in this situation, if the temperature along the fin is increasing, which is not what I expect, but let's say it was positive, then heat flows from right to left. Temperature increases from left to right, then heat flows from right to left, high temperature to low temperature. That's the reason we have a negative sign. And K is called thermal conductivity. So K being higher means for the same temperature difference, you will see a higher heat getting conducted in or out. Okay. So this was given by Fourier, and remember that this is actually not a law of nature. This was just given because it works well. So it's called the gradient diffusion law. Typically, that it's the first derivative that is responsible for conducting heat or diffusing the because of diffusion process. Heat conduction is also a diffusion process, but this is not a law of nature. We have not been able to show this using some other physical law. It was just a mathematical hypothesis given, which works, still working till today. Many people have questioned that why is it d theta, why not d2 theta and so on. So these questions have appeared, but this works the best. That's it. Okay, it's a very interesting idea again, that just given by Fourier in 18th century, very long ago, and still we are using it because that works quite well. Right. So now we have both these tools available, so and both these laws available. So now in this infinitesimal situation that we have, we can just quantify, we can put in the mathematical expression and get an equation out of it, hopefully. Let's see. So let's work here in the figure. So what is the Q? So let's call it Q conduction in. So that is the heat in has to be now. Let's just draw the figure again, because Q stands for flux. I want to talk in terms of watt, so I have to multiply things by area. So the amount of heat per unit time entering because of conduction is the Q conduction in times the cross sectional area. A is the cross sectional area, right, whatever it is, and the heat getting conducted out is Q conduction out times the cross sectional area. Now rather than saying Q conduction in, I am using a symbol Qx in, it's at a distance x, and the Q conduction out, I say Qx plus delta x out. So Qx stands for the heat conducting at the surface which is at a distance of x from the left hand side where we are the origin, and Qx plus delta x stands for the heat getting conducted through a surface which is at x plus delta x, right, because the thickness of this element was delta x. So we, on the right hand side, we have Qx plus delta x, and the convection that's happening from the boundaries is simply Q convection times the area. Now this area is different from A. A is the cross section area, so on the surface it has to be the surface area. And what is the surface area? Surface area is nothing but the perimeter of the surface times delta x. So we will call it P times delta x, right, just to ensure that we don't get confused with the surface area of the fin from which the convection is happening. So we use Taylor series here. So Q at x plus delta x, okay, we will expand that around Qx. Now we are assuming that the function Q as a function of x at distance x or at any distance is infinitely smooth. So we can take as many derivatives as we want. Right. In many cases you will see a small x written here as well, like I had earlier. I removed it. That is because actually heat flux is a vector. Now I don't want to go there right now. That is better discussed in a heat transfer course. So heat flux has three components: Q in the x direction, y direction, and z direction. But for now, since we are working with a 1D situation, that issue does not even arise. So I will not talk about it. The modeling process becomes a bit more intricate, that's it. Okay, so with this I can now substitute that in the overall balance. So what is the overall balance? The overall balance says that Q at x is entering, so that's a positive sign, and Q at x times A, Q at x plus delta x is leaving, so that's a negative sign, and then we also have Q convection times P times delta x leaving, and that is 0. So this is the energy balance equation. So what I will do is I will substitute the Taylor expression that I have written for Qx plus delta x in this equation, and also substitute the Q convection expression, and that will give us the equation for the model equation for this problem. I will skip those steps, you can do it yourself, and I will write the final equation that we have. So, we have a delta x common, so I can divide everything by delta x. So, this delta x simply goes away, so I will remove that from both expressions, and this is the equation that we have. Now, remember that we are trying to find the model equation. The CFD has not even started yet. So, model equation is for situations where delta x will tend to 0. Remember your calculus, you start with a delta x and then you take a limit delta x tends to 0, you get the model equation. So, here again please do not confuse CFD starts after this, and sometimes CFD process is initiated even before we take the limit delta x tends to 0, but we will discuss that later. So, for now we are modeling the problem, so we will model it for a continuous situation where delta x actually will tend to 0 in the model equation to get the model equation. So, in the limit delta x tends to 0, what we get is dq by dx times a okay. So, this is our model equation. Now, q again can be written using Fourier's law in terms of temperature theta, and that was minus k times d theta by dx So, what I will do now is I will also assume that the thermal conductivity is homogeneous, and you may have started guessing that this is your diffusion term in the common equation that we had started the course with, right, except that it is a 1D situation. So, rather than having divergence of gamma times gradient of phi, we have d by dx of minus k times d theta by dx. So, if I assume homogeneous k, then I can simply take the k out of the derivative. So, this becomes minus a times and let us divide every thing by k times a. Right. This is our governing differential equation for the problem. That is not Laplace's equation. What is it called? This has got a mathematical name. Anybody knows that? Any answer? Yeah, Poisson equation. So, whenever you have a second order derivative equals to some function of something, it is called a Poisson equation. Typically, on the right hand side you have a function of x, y and z, you do not have a theta, but let us put the theta term there as well and call it a Poisson equation. Okay. But the name does not really matter. If you want to remember it, that is fine. Right. So, under what conditions does it become a Laplace's equation? Exactly, if theta is equal to theta f. So, if the surface temperature is the same as fluid temperature, or what we are saying is there is no convection happening, this theta minus theta f appeared because convection loss was there from the surface. if for some reason on the surface you had insulated the surface, you put a coating of insulation material on the surface, there is no heat loss from the surface, so that becomes a Laplace's equation, only heat conduction. So this is our governing differential equation for the problem. Now, is this problem well posed, or do we need something else to make it well posed? If I solve this, will I get a unique solution, or do we need boundary conditions? We need boundary condition. It's a second order equation in one dimension, so I need two boundary conditions, on the left surface and the right surface, on the left boundary, the right boundary. So we need boundary conditions. Now boundary conditions depend on the situation. So let's say on the left hand side, which is theta at x equal to 0, where the fin starts on the surface, the temperature is known. Let's say you know the temperature as some theta naught tilde. So that's the temperature on the left surface on which the fin was attached. And then you also have x equal to L, that is the end of the fin. So let's say that the end of the fin is insulated for simplicity. So if it's insulated, then what we are saying is there is no conduction out from the right surface, right. So if there is no conduction out, then what it means is minus k times d theta by dx at x equal to L is 0, because Fourier's law of heat conduction says that Q conduction is minus k d theta by dx. So that basically means that d theta by dx at x equal to L is 0. So this boundary condition, one is of the type Dirichlet boundary condition, and the one on the right hand side is called the Neumann boundary condition. Dirichlet is where you specify the value of the unknown, and Neumann is where you specify the value of the derivative. Now in this case the value of derivative is 0, so it is called homogeneous Neumann. We know homogeneous in differential equations used when the right hand side is 0. So it's called a homogeneous Neumann boundary condition. So sometimes some books, some literature or some places you will see that it's written boundary condition on the right hand side is homogeneous Neumann for temperature. So that basically means it's an insulated surface where the heat conduction is 0. So that's d theta by dx is 0. So that is the process of modeling. Did you understand that? Any question on this? So in a heat conduction course, this will be discussed over 1 or 2 lectures. We did it quite quickly because that's just an intermediate step for us. Our job starts now. Well, now it's actually not that difficult because we have the equation, the governing differential equation. Now governing differential equation is applicable everywhere, just remember that. So you can apply it's basically obtained from the physical laws or laws of heat conduction and convection. So along any distance along the length of the fin you can apply the equation. Sometimes we get confused, where is it applicable? It's applicable everywhere, including the boundaries actually, but for boundary we have boundary conditions which actually are much more helpful, so we will use that for boundaries. But this equation is applicable everywhere along the surface of the fin, along the length of the fin. It's a 1D problem. So let's discretize the governing differential equation. So the first step, once we have an equation, a model equation to work with, is discretization. So we have a second order derivative. Now where are we discretizing the equation? The equation is applicable everywhere along the length. So let's choose any arbitrary distance xi. So hp by k is just a constant. No? H is again a constant for a given situation, p, k, a, some geometrical parameters or some physical parameters. So let's call it beta. So now what I do is I move the theta I term on the left hand side, because theta I is actually an unknown temperature at the location xi.
सर जो इक्वेशन मिल रहा है ये डिफ्यूजन इक्वेशन है, पर पहले ही हम अज्यूम कर चुके हैं कि जो कंडक्शन हो रहा है सिर्फ एफ डायरेक्शन में, जबकि डिफ्यूजन हमें मिल रहा है हम मान रहे हैं कंडक्शन सिर्फ एफ डायरेक्शन में, कैसे ये पॉसिबल है? पहले हम अज्यूम कर चुके थे कि
let me finish this, then I'll answer your question. Okay, so let me finish this whole process. So what we do is we combine, this is also a theta I term, this is also theta I term. So we combine this two. So what we get is this. Actually better if I write plus and then I put negative signs inside. So this is the difference equation for the problem. Now what are the unknowns in this equation? Every equation has a set of unknowns that you are solving for. What are the unknowns in this equation? Theta f. Theta f is known, fluid temperature is known. Are you asking or delta? Delta x. No, delta x is again set by us. It's theta I minus 1, theta I plus 1 and theta I also. You don't know the temperature, that is what you're solving for, right? So we are solving this problem for the temperature along the length of the fin. So we want to solve for these thetas. But remember, we did the discretization at the point xi, and how many intervals do we have? Well, we have intervals which were in our choice. So we have taken theta 1, theta 2, theta 3 all the way to, let's say we have theta n here. It starts from theta naught. So how many intervals do we have? N plus 1. Right. So well, n or n plus 1? N intervals is what we have. So we have a total of n intervals. So you can find, if you know the length, you can find delta x. So all I have to do is I have to fix a capital N value, and based on that I will be able to find delta x and also how many theta unknown thetas are there. So how many unknown thetas are there? N plus 1? N plus 1. So you have a total of, you have discretized the problem, so it goes from theta naught all the way to theta n. Temperature har jagah find, if you want to find the temperature everywhere, you want to find all the temperature values. Let's for now let's say that we don't know them. Okay. So what we will do is for the knowledge of boundaries what we have, we will include that as extra equations. So the total number of thetas that we have is n plus 1 in this situation. So if you have n plus 1 unknowns, how many equations do you want? Linear equations, n plus 1, right? So how many equations do we actually have here? If we apply the governing differential equation on all the interior points, how many equations do we have? N minus 1. How many interior points do you have? We have interior points starting from theta 1 all the way to theta n minus 1. Theta naught and theta n are boundary points. So for now what we are saying is we are applying the governing differential equation on the interior points in this case. So we have a total of n minus 1 equations, and we have two boundary conditions, so that makes it n plus 1 conditions. So n plus 1 unknowns, n plus 1 conditions, we should be able to solve it. So in the next lecture, which is day after tomorrow, we will continue from here. We'll formulate the linear system and then we'll solve it. So the class day after tomorrow, we'll have it in the lab downstairs. Everybody knows about the PC lab, which is just below this floor. You can read the board. We'll have it there. I'll book it and I'll let you know over the course mailing list. Everybody is getting was getting mails through the mailing list. Okay, on Moodle there's an announcement section. If you click it, there are certain announcements. So we also have a Google Chat page for this course. So because of registration, sometimes mailing list does not include everyone. So what you can do is you can join the Google Chat spaces, and then I'll put all the announcements there. That is much easier. Okay. Right. So day after tomorrow we'll have a lab. So you don't need to bring your computers. We have PCs there. You will be using Python. First couple of minutes we'll formulate the linear system. Then we'll start solving it using Python right away. Thank you.